Okay, today we're going to make a start on Year 13 differentiation. And before we go any further, I just wanted to recap a little bit on what differentiation was from Year 12. So recall we've got some kind of function. Let's say this is y equals f of x. And we've got some x value, let's say here. And we've got some x value, let's say over here. Let's call this point x. Let's call this distance here h, which makes this point here x plus h. And what we want to do is we want to find the gradient of this chord. So this is a chord. The chord is a straight line joining 2 points on a curve. So this coordinate here is going to be x, f of x. And this coordinate here is going to be x plus h, f of x plus h. Okay. Now the gradient of the chord then, fairly easy to calculate. So the gradient of the chord is just rise over run. Difference in y, which in this case is going to be f of x plus h minus f of x. So that's the difference between that point and that point. Divided by the run, which is x plus h minus x. Of course, the two x's cancel, and we're left with f of x plus h minus f of x, all divided by h. That's the gradient of the chord in green. And now once we've got that, what we want to do is we want to take this point here and we want to bring it down the curve so the chord moves. So we're varying h, and as this point gets closer and closer and closer to the other point, then the chord will begin to map closely onto this line here, which is the tangent, until such a point where in the limit, as h goes to 0, i.e. this point maps on top of that point, the chord becomes the tangent, or at least the gradient of the chord becomes the gradient of the tangent. So we would say the gradient of the tangent, which is what differentiation is all about, is equal to the gradient of the chord in the limit as we take h to 0. And this is the definition that is in the LXL formula book, and is a very common definition for differentiation. And we use that to differentiate things from first principles. The limit as h goes to 0 of f of x plus h minus f of x divided by h. And if you plugged in h is 0 into that, you would get 0 divided by 0, which doesn't make any sense. It's indeterminate. So you need to look at the functions and how they behave to actually get a function back out of that. Okay. So I'm going to use that to derive some new differentials. The first one we have met in year 12. And then the other 3 will be new, well, 2 will be new, and then 1 I'm not going to use that on. But I'm going to give you anyway. I'll prove the other one, which is the log, in implicit differentiation a bit later on in the course. So let's look at the exponential first. So let's say y equals e to the x. So the dy by dx then, this is the differential of y with respect to x. That is going to be equal to the limit as h goes to 0 of e to the x plus h. So we're going to plug in x plus h in for x, e to the x plus h, minus f of x, which is e to the x, all divided by h. Now we need to know something called the Taylor series for e. So we're going to say e to the h is approximately 1 plus h plus a half h squared. It does carry on. Next one will be a plus a 6th h cubed, plus a 24th h to the 4, and so on. But I'm just going to use the first few terms there. So I know technically that is derived from the differential. It's a circular definition, but For the A-level course, it's okay. You don't need to know derivation anyway, but I'm just going to justify it here. Using that, so dy by dx then is equal to the limit as h tends to 0 of e to the x times e to the h minus e to the x, all divided by h. Now I can use my definition for e to the h. Because h is going to go to 0, then all of these kind of high order terms, they become insignificant. They go to 0 much quicker than these ones, so these ones will dominate. So that's going to equal the limit as h tends to 0 of e to the x times 1 plus h plus, don't actually need the rest, minus e to the x all divided by h. And that is going to equal the limit as h tends to 0 of e to the x minus e to the x is this 0, they cancel out. So we've got h e to the x. I will put the quadratic term in, so it's plus a half h squared e to the x, and so on. All divided by h. But all of these so on terms are going to contain higher and higher powers of h. The only one that's going to cancel is this first one. That's the limit as h goes to 0 of, and now all of the terms on the top of the fraction have got h in it, so I can bring the h from the bottom in. So that's going to be just e to the x. That's going to be half h e to the x plus dot dot dot. And all of these terms are still going to have a h in it. So when h goes to 0 now, they will all disappear, and we're just left with e to the x. Now that is a year 12 derivative. This is a function that differentiates to itself. The differential of e to the x is e to the x. Okay. All right, two other ones which are going to be new. So let's say y equals sine of x. Okay. So using our differentiation from first principles definition, dy by dx is going to equal the limit as h tends to 0 of f of x plus h, so that's going to be sine of x plus h, minus f of x, which is sine of x, all divided by h. Now this is something that you do need to be able to do in the A-level course, so make sure you can understand this one. So y prime then is going to be the limit as h tends to 0 of, and we can use the compound angle formula on that. Okay, so if you've done your year 13 trigonometry already, you would have met the compound angle formulae. So that's going to be sine of x times cos of h plus sine of h times cos of x, and don't forget the minus sine of x. And that's all still divided by h. But you'll also recall that when h is small, which is what we're doing because we're taking h to be 0, sine of h is approximately h, and cos of h is approximately 1 minus half h squared. Okay. So we can use these two definitions in place up here because h is small, so we can justify using these. So this is going to tell us that y primed is now the limit as h tends to 0 of this thing times sine of x, so that's going to be sine of x times 1, sine of x. Sine of x times that thing, so it's minus a half h squared sine of x. Then we've got h times cos of x, plus h times cosine of x. And then we've got minus sine of x there. That's all divided by h. Okay, almost there now. We can see, once again, the sine of x, like the e to the x before, is going to cancel. So the sine of x minus sine of x disappears. Everything now contains a h in the top. So that's minus a half h times sine of x plus the cosine of x. And now there's no fraction, we can take h to be 0. And if h becomes 0, that disappears. And we're left with the cosine of x. That might have been a surprising fact to you, or you might have looked it up beforehand, but here we go, we can see that sine of x differentiates to cos of x, and this is the proof using first principles, which you do need to know for the course. You do need to know how to do differentiation from first principles for polynomials, sine and cosine. The other thing to mention here is these are only true when h is measured in radians. So therefore this is only true when x is measured in radians. If you're not in radians and you're in degrees, then actually you get a nasty coefficient kicking around, which will just get in the way. Okay, radians is the most natural measure for measuring angles, and this is essentially why, because the calculus says that then sine of x differentiates to cos of x with no stupid coefficients kicking around. The next one is cosine of x. I'll do this one a little bit quicker. So y equals cos of x. That means y primed is going to be the limit of cos of x plus h minus cos of x, all divided by h, which equals the limit as h tends to 0 of cos of x, cos of h minus sine of x, sine of h minus cos of x. So that's again using the compound angle formula, but this time for the cosine of x. So that's going to equal the limit as h goes to 0 of, that is going to be 1 minus a half h squared. So that's cos of x minus a half h squared cos of x. Sine of x, sine of h is going to go to h, that's just minus h times sine of x. Don't forget your cos of x, all divided by h. And again, cos of x is cancel, h will cancel there, and one of those, that's the limit then, as h goes to 0 of minus a half h cosine of x minus sine of x, and I can take h to be 0 now, that disappears, and I'm left with minus sine of x. So cos differentiates to minus sine. Again, this is only true in radians. It must be in radians. Before we go any further, let's just have a look at these graphs, just to see if we can justify it using the graphs as well, just to give us some idea that we're doing something right. There's my graph of sine of x. This point here is pi. This point here is 2 pi. Don't forget we're in radians. Now the gradient of the sine curve at the origin is positive. The gradient at the peak is 0, the gradient at this point here is negative, the gradient at this point here is 0, and the gradient at this point here is positive. And we can kind of see that that is indeed a cosine curve. And if we differentiate the cosine curve, again, look at the gradients. The gradient of that is 0, the gradient here is negative, the gradient here is 0, the gradient here is positive, and the gradient here is 0. We end up with the negative sign. So it's minus sine of x. This one was the cosine of x. This one was the sine of x up here. And we could do the fourth one as well. The gradient there is positive. Sorry, the gradient there is negative even. Gradient there is 0. Gradient there is positive. Gradient there is 0. Gradient there is negative. And we will end up with, really badly now, but minus the cosine curve. And you differentiate that, you'll get back to the original sine curve again. So it's a cyclic differential, and you differentiate one of these trig functions 4 times, you get back to the original. Okay, a bit of a summary then on all the derivatives that we need to know as a general case. We've got the polynomial differentiation from year 12, so a constant times a variable to the power of a constant. Doesn't have to be an integer. what we do is we multiply by the power, so the n comes down as a multiplication, and then we subtract 1 from the power. That was year 12, that's pretty much the only thing you did in year 12 in that chapter anyway. Exponential, which was met at the end of year 12 very briefly. AE to the kx, if you have a multiplier times the x, then that comes down as a multiplier at the front. So in the example I did from first principles, k was the number 1, so it just went from e to the x to e to the x. There's our sine one again. I've popped in some extra letters in here, so a constant multiplier a and a constant multiplier k, and we can see that the k has come out of the cosine, but it's still in the sine. And with all of these three, the exponential, the cosine and the sine, whatever was in the exponent remains in the exponent. Whatever was in the trig function stays in the trig function. It doesn't change, okay? That's important, and a common mistake made by students first kind of playing with differentiation of these functions. And finally, this one here, which I haven't looked at yet, and I will prove for you when we do implicit differentiation towards the end of the chapter. You can't do this one very easily with from first principles. But essentially, it's a times the natural log of k times x, and that goes to a on x. And it's not a typo or a righto. K does genuinely disappear. And these are all true for any constants a, n, or k. Okay, a, n, and k are all constants in these. And if you remember these 5 rules for differentiation, combined with the 3 methods for differentiation that are coming, then you can't go too far wrong in this topic. Okay, so I want to justify why this k disappears. So I've got 2 justification reasons why the k disappears. So let's just have a look at one of them now, and then the other one we'll look at when we do the chain rule a bit later on in the course. In fact, I think that might even be my next video. So what I'm going to do is I'm just going to use a log law here to say that this is a times the natural log of k. In fact, I'll put that in there. Then plus the natural log of x. It's a log law. Okay, if you've got a product of 2 things in a log, you can split them out into 2 separate logs with an addition. So that is going to be a times the natural log of k plus a times the natural log of x. So when we differentiate this, dy by dx, that is going to go to the a on x as promised. Okay, that's the definition. You need to know that. Okay, a log x goes to a on x. But this, a and k, well, they're both constants. So therefore, a log k is a constant. So that just disappears. It's a constant. Okay, and constants disappear under differentiation. Okay, so there's a kind of an algebraic argument as to why that disappears. All k does is it moves the graph vertically upwards. So as we increase k, it will move it up. That doesn't change the derivative. Okay. Next video, I will justify why, another reason why it's a on x using a substitution in the chain rule. Okay. So yeah, that's the beginnings of differentiation. Those 5 types of functions: polynomials, exponentials, sines, cosines, and logs. You need to know how to differentiate all of those for the rest of the course. Okay.